In this segment, we're going to look at another method to achieve chosen plaintext security that's actually superior to CBC. And this method is called randomized counter mode. Unlike CBC, randomized counter mode uses a secure PRF. It doesn't need a block cipher. It's enough for counter mode to just use a PRF, because we're never going to be inverting this function f. So we're going to let f be the secure PRF, and it acts on n-bit blocks. Again, if we use AES, n would be 128. And the way the encryption algorithm works in counter mode is it starts off by choosing a random IV. It's a 128-bit random IV in the case of AES. And then essentially we start counting from this random IV. So you notice the first encryption is of IV, then of IV plus 1, up to IV plus L. So we generate this random pad. We XOR the result with the message, and that gives us the ciphertext. And as usual, you notice that the IV here is included along with the ciphertext, so that in fact the ciphertext is a little longer than the original plaintext. And the point, of course, is that the encryption algorithm chooses a new IV for every message, and so even if I encrypt the same message twice, I'm going to get different resulting ciphertexts. One thing to note is that this mode is completely parallelizable, unlike CBC. CBC was sequential. In other words, you couldn't encrypt block number 5 until you've encrypted blocks number 1 to 4. So hardware companies who might have multiple AES engines working in parallel cannot actually use those AES engines when using CBC, because CBC is inherently sequential. So even though you might have 2 or 3 or 4 AES engines, you can only use one of them when doing CBC encryption. With counter mode, everything is completely parallelizable. If you have 3 AES engines, encryption basically will work 3 times as fast. So that's the beauty of counter mode. And counter mode also has a corresponding nonce-based counter mode, where the IV is not truly random, but rather is just a nonce, which could be a counter. And the way you would implement nonce-based counter mode is you would take the 128 bits block that's used in AES, and then you would split it in two. You would use the left 64 bits as the nonce, so the counter, say, would count from 0 to 2 to the 64, and then that will be the nonce part of it. And then once you specify the nonce, the lower order 64 bits would be doing the counting inside of the counter mode encryption. Okay, so nonce goes on the left, and the counter mode encryption counter goes on the right. And it's perfectly fine if this nonce is unpredictable. The only restriction is that you encrypted most 2 to the 64 blocks using one particular nonce. The danger is that you don't want this counter to reset to 0, so that then you will have 2 blocks, say this guy and this guy, that are encrypted using the same one-time pad, namely this one and this one. So let's quickly state the security theorem for randomized counter mode. By now you should be used to these kind of theorems. Basically, we are given a secure PRF. What we end up with is an encryption scheme. We'll call it E sub CTR, E sub counter mode, which is semantically secure under a chosen plaintext attack. It encrypts messages that are L blocks long and produces ciphertexts that are L plus 1 blocks long, because the IV has to be included in the ciphertext. This is for randomized counter mode. And then the error bounds are stated over here. It's basically the same bounds as in the case of CBC encryption. As usual, we argue that this term is negligible because the PRF is secure, and we would like to deduce from that that this term is negligible so that eCTR is secure. Unfortunately, we have this error term here, and so we have to make sure this error term is negligible, and for that we have to make sure that Q squared L is less than the size of the block. We remember Q is the number of messages encrypted under a particular key, and L is the maximum length of those messages. Now, interestingly, in the case of CBC, we had Q squared L squared had to be less than X, which is actually worse than we have for counter modes. In other words, counter modes can actually be used for more blocks than CBC could. And let's see a quick example of that. So here's again the error term for counter mode. Remember, Q is again the number of messages encrypted with the key, and L is the length of those messages. And as before, just as in the case of CBC, suppose we want the adversary's advantage to be at most 1 or 2 to the 32. That basically requires that this Q squared L over X be less than 1 over 2 to the 32. And so for AES, what happens is if you plug in the values, X is 2 to the 128, 128-bit blocks. So Q times square root of L should be less than 2 to the 48. This is basically the bound you get from plugging in 2 to the 128 into this bound here. And as a result, you can see if you're encrypting messages that are each 2 to the 32 blocks, then after 2 to the 32 such messages, you have to replace your secret key, otherwise randomized counter mode is no longer CPA secure. So this means we could encrypt a total of 2 to the 64 AES blocks using a single secret key. Remember, for CBC, corresponding value was 2 to the 48 blocks. So in fact, because counter mode has a better security parameterization, in fact we can use the same key to encrypt more blocks with counter mode than we could with CBC. So I wanted to do a quick comparison of counter mode and CBC and argue that in every single aspect counter mode is superior to CBC, and that's actually why most modern encryption schemes actually are starting to migrate to counter mode and abandon CBC, even though CBC is still quite widely used. So let's look at the comparison. First of all, recall that CBC actually had to use a block cipher, because if you look at the decryption circuit actually ran the block cipher in reverse. It was actually using the decryption capabilities of the block cipher. Whereas counter mode, we only need a PRF. We never ever use the decryption capabilities of the block cipher. We only use it in the forward direction, only encrypt with it. Because of this, counter mode is actually more general, and it can use primitives like salsa, for example. Salsa 20, if you remember, is a PRF, but is not a PRP. So counter mode can use salsa, but CBC cannot. And in that sense, counter mode is more general than CBC. Counter mode, as we said, is actually parallel, whereas CBC is a very sequential process. We said that counter mode is more secure. The security bounds, the error terms are better for counter modes than they are for CBC, and as a result you can use a key to encrypt more blocks in counter mode than you could with CBC. The other issue is, remember in CBC we talked about the dummy padding block. If you have a message that's a multiple of the block length, in CBC we said that we had to add a dummy block, whereas in counter mode this wasn't necessary. Although I did want to mention that there is a variation of CBC called CBC with ciphertext stealing that actually avoids the dummy block issue. So for standardized CBC we actually need a dummy block, but in fact there is a modification to CBC that doesn't need a dummy block, just like counter mode. Finally, suppose you're encrypting just a stream of 1 byte messages and using nonce-based encryption with an implicit nonce. So the nonce is not included in the ciphertext. In this case, every single 1 byte message would have to be expanded into a 16 byte block and then encrypted, and the result would be a 16 byte block. So if you have like a stream of 100 1 byte messages, each one separately would have to become a 16 byte block, and you'll end up with a stream of 100 16 byte ciphertexts. So you get a 16x expansion on the length of the ciphertext compared to the length of the plaintext. In counter mode, of course, this is not a problem. You would just encrypt each 1 byte message by XORing it with the first byte of the stream that's generated in counter mode. So every ciphertext would just be 1 byte, just like the corresponding plaintext. And so no expansion at all using counter mode. So you see that essentially in every single aspect, counter mode dominates CBC, and that's why it's actually the recommended mode to be using today. Okay, so this concludes our discussion of chosen plaintext security. I wanted to just quickly summarize and remind you that we're going to be using these PRP and PRF abstractions of block ciphers throughout. This is actually the correct way of thinking of block ciphers, and so we'll always think of them as either pseudo-random permutations or pseudo-random functions. And then I wanted to remind you again that so far we saw 2 notions of security. Both only provide security against eavesdropping. They don't provide security against tampering with the ciphertext. One was used when the key is only used to encrypt a single message. The other one was used when the key was used to encrypt multiple messages. And as we said, because neither one is designed to defend against tampering, neither one provides data integrity. And we're going to see that this is a real problem. And as a result, in fact, I'm going to say in the next segment that these modes actually should never ever be used. You should only be using these modes in addition to an integrity mechanism, which is our next topic. Okay, so far we've seen basically if you're using the key once, you can use stream ciphers or you can use deterministic counter mode. If you're going to use the key many times, you could use randomized CBC or randomized counter mode. And we're going to talk about how to provide integrity and confidentiality once we cover the topic of integrity, which is our next module.